All right, let's get straight into it. We're breaking down a really interesting new framework from Meta AI. This is all about securing agentic AI systems. We're talking practical, no fluff, pure tech. So here's the game plan. We'll kick things off with the agent's core dilemma, then pinpoint the properties that make them high stakes. After that, we'll introduce the rule of two itself, see how it actually works, and finally, touch on its limits and where we go from here. First up, the agent's dilemma. And look, the key thing to get here is that the big security challenge we face isn't some bug we can just patch. No, it's a fundamental vulnerability that's baked right into the very nature of autonomous AI as it exists today. Okay, to make this real, let's think about a hypothetical agent. We'll call it EmailBot. You know, an AI that can read your inbox, access your stuff, and reply for you. It's the perfect example because it shows both sides of the coin, the incredible power and the incredible risk. So, the elephant in the room here is, of course, prompt injection. I don't need to tell you guys, this is the fundamental, unsolved weakness of LLMs right now. You feed it untrustworthy data, and boom, it can hijack the model, making it completely ignore its safety instructions and do whatever an attacker wants. And here's how easy that attack chain can be. Step 1. An attacker embeds a malicious payload, say in a spam email. Step 2. Our email bot picks it up and processes it. And Step 3. The agent gets hijacked and starts exfiltrating your sensitive data. It's really just a classic input vulnerability, but now supercharged with the power of an LLM. Okay, so that's the setup. Now let's get into what makes this so dangerous. The paper argues that the real catastrophic risk doesn't come from any one thing an agent can do. Instead, it's about a specific, toxic combination of 3 capabilities, what they call the lethal trifecta. First up, property A. This is simple. The agent can process untrustworthy inputs. We're talking anything from the outside world, inbound emails, stuff it scrapes from the internet, you name it. This is your front door for an attack. Next, property B. The agent has access to sensitive data or systems. Think about it. Your entire email history, private documents, maybe even internal company databases. This is the prize. This is what the attacker wants. And finally, property C. The agent can actually do stuff. It can take actions in the real world, send an email, make an API call, change a setting. This is the weapon. This is how the damage gets done. So let's put it all together. You've got A, untrusted input, B, access to private data, and C, the ability to take external actions. When an agent has all 3 of these capabilities at the same time in the same session, well, that's the lethal trifecta. That's when you have the perfect storm for a maximum impact security failure. Which brings us to the solution proposed in this paper, the agent's rule of 2. And what's so cool about this is that it's not another probabilistic defense, another filter that might work. No, this is a deterministic framework. It's designed to structurally break the attack chain. So here's the rule, and it's beautifully simple. The paper basically says, look, we can't reliably stop prompt injection yet. So until we can, the rule is this. An agent can have any 2 of those 3 high-stakes properties, but never all 3 at the same time, within the same session. Pick 2. Let's go back to our email bot example. How does this rule help? Well, you get 3 secure options. First, a BC config. You get rid of A, untrusted input. Maybe the bot only reads emails from a pre-approved safe list. Or you could go with an AC config. Get rid of B, private data access. The bot can browse the web and send emails, but it has 0 access to your sensitive inbox, so who cares if it gets hijacked? And finally, the AB config. Get rid of C, external action. The bot can read everything, but it needs your explicit OK before it sends a single email. See, each option breaks that lethal chain. Okay, so that's the theory. Now let's see how the rule of 2 actually plays out in practice with a few different types of agents. This table breaks it down nicely. Think of a travel agent. It's got to process untrusted info from the web, A, and it might access some of your user info, B. So to be safe, we disable, C. It needs you to click confirm before it actually books anything. Then you have a research assistant. It can browse the web, A, and use tools, C, but we keep it safe by sandboxing it, completely walling it off from any private user info, B. And finally, an internal coder agent. This one might need access to sensitive code bases, B, and the ability to commit changes, C. So the only way to make it safe is to completely cut it off from untrusted input, A. It only works with verified internal data sources. Now, let's be real for a second. This is a great framework, but it's not a silver bullet. It's designed to mitigate one very specific, very dangerous threat. It's not a whole security program in a box. So let's talk about the limitations.
Yeah, this has to be just one piece of your defense in depth puzzle. It absolutely does not replace good old-fashioned principles like least privilege, and it does nothing to protect against other AI risks, like just plain old hallucinations or the agent making a mistake. Plus, you have to remember that some of these controls can fail. That human in the loop, that only works if the user isn't just blindly clicking approve on everything, and we all know approval fatigue is a very real thing.
So what's next? Well, the really interesting work is focused on making this whole framework more dynamic. We're talking about things like security-aware protocols, so agents can interact safely. And this is cool, research into supervisory agents, like Meta's Llama firewall concept, that could replace the human for approvals but do it safely at machine speed. The holy grail here is finding a way for an agent to safely switch between these configurations mid-session. Like, it could be an AC agent 1 minute, then safely transition to being a BC agent the next, without ever having all 3 properties active at once.
And that leaves us with the big, multi-million-dollar question, doesn't it? As we build these supervisory agents to watch over our other agents, are we actually solving the problem, or are we just trading a simple vulnerability for a much more complex and maybe even more dangerous one? That's really the fundamental challenge we're all going to have to tackle as we build out these incredibly powerful systems.